Hey class. Okay, let me get back to the beginning. So today we're going to talk about 5.4. We actually only have two more sections left, 5.4 and I think the last one is 7.4. This is actually a topic we touched on in class a couple months ago, the orthogonal diagonalization of symmetric matrices. We didn't approach it this way, but the big theorem in here is something that I mentioned when we were playing with correlation matrices. So certain things happen if you're dealing with a symmetric matrix. And if I could find my thing. So here we were playing with a simple symmetric matrix. I just have one on the diagonals, and then I can change the number in the off diagonals. And here we can see the transformation as I move this, as I change this number. It stretches it in one dimension and shrinks it in another dimension. And those dimensions that it stretches and shrinks are perpendicular to each other. So it looks like it stretches it in the direction y equals x and shrinks it in the direction y equals negative x. And we can change that a little bit. So here, now my correlations are negative, so that it's stretching it in the direction y equals a negative x and shrinking it in the direction y equals x. If you don't limit the diagonals to be 1, then you can stretch it in both directions or shrink it in both directions. But the thing here is the direction that it stretches and the direction that it shrinks are orthogonal. So that seems to say that the eigenvalues of a symmetric matrix are perpendicular to each other. And that's exactly the big theorem of this section, that if you're dealing with a symmetric matrix, we'll just focus on a symmetric matrix with real numbers, or we're not using complex numbers, then you will have real eigenvalues and they will be orthogonal to each other. And that is really nice, because then you can get a diagonalization that's even slicker than what we've been able to do before. More slicker? Don't know the appropriate terminology. So okay, so here they jump in. So remember, if A is a square matrix and we have the eigenvectors v1 to vm corresponding to distinct eigenvalues, then the set is linearly independent. We know they're linearly independent. But if it's a symmetric matrix, we can say even more. We can say what we just talked about. They're not just independent, but the eigenvalues are orthogonal. This does technically only apply to different eigenvalues. So the eigenvalues for the eigenvectors for different eigenvalues are orthogonal. If you have multiple eigenvalues for a single eigenvalue, then those may or may not be orthogonal, and we might have to use Gram-Schmidt to orthogonalize them. But as long as they are different eigenvalues, we know for sure off the bat that they're orthogonal. And here is the proof. They use the fact that A equals A transpose, and they start with v1 dot v2, and they need to show that that's 0, and they do some fancy math. Not really fancy, but they just use the rules and properties that we have. Here's the fact that they use that that an eigenvector of a transpose is the same as the eigenvector for A and A transpose are the same, and here A equals A transpose, so they can rewrite it this way and then keep going, and eventually we get down to the fact that v1 dot v2 has to equal lambda 2 over lambda 1 times v1 dot v2, but lambda 2 over lambda 1, since they're distinct, they can't equal 1, and so the only way for those two things to be equal is for both sides to be 0, and so v1 dot v2 would have to be 0. So that's the proof. You can study it in more detail later. So We've talked about being able to diagonalize a matrix. To be able, A is said to be orthogonally diagonalizable if there's an orthogonal matrix. Before we just had diagonalizable with an invertible matrix, but here it's an orthogonal matrix and D is a diagonal matrix. So P, D, P, T, so the transpose of P, that's the same as P inverse because it's an orthogonal matrix, makes it even slicker because we can just take the transpose, we know the inverse. And the columns of P are all orthonormal. So they create an orthonormal basis. So, and orthogonally diagonalizable matrices are symmetric. And the big theorem says that it's if and only if. So if you have an orthogonally diagonalizable matrix, then that matrix is symmetric. And if you have a symmetric matrix, then it's orthogonally diagonalizable. And this is called the Spectral Theorem. There's a little bit in your book, when you do your reading, there's a little call out that on the side that explains kind of how it got its name. It has to do with actually the vision spectrum of light. So, because the vision spectrum is connected to eigenvalues and eigenvectors. So, to orthogonally diagonalize the matrix, we're going to do the same process as diagonalization. We just have to make sure that things are orthonormal. We don't have to do anything as long as all the eigenvalues are distinct, because by the spectral theorem, they already will be distinct. But if we have multiplicities greater than 1, then we have to check, and we might have to do Gram-Schmidt to make sure it's orthonormal, to create an orthonormal basis. So here we've got a matrix. Let's calculate the eigenvalues. So we subtract lambda off the diagonal, find the characteristic polynomial, factor it down, and we get these 3 eigenvalues. We've got a multiplicity here, so we're going to have to be careful. With lambda equals a -3, we subtract 3i from the diagonal. Subtract 3 from the diagonal. We row reduce to this matrix and find the null space, and we get 2 free variables, and these end up being the basis for the null space. And we are lucky this time because these are already orthogonal, but because these come from an eigenvalue where they have more than multiplicity 1, then we aren't guaranteed that. We just lucked out. So that's what this comment here says. So we still have to do the other eigenvalue. We subtract 1 off the diagonal, row reduce. We end up with a one-dimensional null space. The basis for the null space is this one, and this vector is orthogonal to the other ones. That's what the spectral theorem says, or the theorem before that we talked about. It's not the spectral theorem, but this theorem says that the eigenvectors of distinct matrices for a symmetric matrix are always orthogonal. Okay, and you can test it. 1, 0, 1. If you dot it with this one, it's going to be 0. Dot it with this one, it's going to be 0. So, very nice. And now we can use that to use those 3 vectors to create our P, like our orthogonal matrix, to complete our orthogonal diagonalization of A. So we have 3 orthogonal vectors, but we need to make them orthonormal, so we divide by the length of each one. And this one's easy. Here you end up with lengths of 2, so you have to divide by the square. So the length of the square root of 2, so you divide by the square root of 2. And now you can create P with the 3 orthonormal vectors. again, you've got to be careful to make sure that things line up. So these first two vectors correspond to the eigenvalue of a -3. The last one corresponds to the eigenvalue of 1. And finding the inverse of p is easy. Boom, we transpose it, and we can write A as that. So it's very nice. What this means is that there is a rotation, or it might be a reflection in there too, but the transformation by p transpose of a vector won't change lengths and won't change angles, and then that puts it into the new basis, and in that new basis you'll stretch it in these dimensions along those eigenvectors. So you'll stretch it a -3 in one, a -3 in another, and 1 in another, and then you rotate it and reflect it back to where it was, or reflect it. So really nice. Nice simple transformation, simple to kind of understand what's going on compared to some other transformations. So here's another example. So it starts off the same. Let's find the eigenvalues. Again, this one, we can tell from the bat that it's not invertible, so we're going to end up with 0 as an eigenvalue. And in fact, we end up with 0 twice. 55 is the other one. And so we subtract 0 from the diagonal, row reduce. We get these two vectors as a basis for the null space. And in this case, we are not so lucky. These are not orthonormal. They're not orthogonal, so we have to do the Gram-Schmidt. So we're going to take V1, and then we're going to take V2 and subtract the projection of it onto V1 to create our new orthogonal vector. That is illustrated here. Okay, so V1 is fine. We can keep one of them. And then we're going to use the other one to take the piece of the other one that's orthogonal to a -1, 1, 0. And that's what the Gram-Schmidt does. So take the projection onto the first and subtract it from V2, and we get a vector that's orthogonal to V1. Now 55, we subtract 55 from the diagonal. Row reduce. We've got a one-dimensional row space. One-dimensional null space, and we get a basis for that null space. And so now we have our three vectors. We have this one, and this one here. V1, V2, W3. So really we're doing W2, I guess. So because V2 was the first one we got out and we had to normalize. So and we normalize those by dividing by the lengths, and now we have three vectors. They all have unit lengths, and they create an orthonormal basis for our 3. And now we can write down P, and we can write down D, and so we can write down, if we want, PDP transpose, and we know what B is. So pretty slick. Again, these first two match up to the zero eigenvalues on the diagonal. Last one matches up with 55. So I think there's one more idea here. Yep, the spectral theorem, more in depth. So an n by n symmetric matrix. This only applies to a symmetric matrix. It has the following properties. A has n real eigenvalues, counting multiplicities. So we haven't had you guys deal with matrices that have non-real eigenvalues, like complex ones or imaginary ones. But symmetric ones have, as long as the entries are real, the eigenvalues will be real. The dimension of the eigenspace for each eigenvalue is equal to the multiplicity of lambda. So this, we don't have to worry about that. Does the algebraic multiplicity equal the geometric multiplicity thing? As long as we have an n by n symmetric matrix, I think we have to also add that it has real eigenvalues. Then we always, it's always diagonalizable. We always get the geometric multiplicity that we need to match the algebraic multiplicity of all the eigenvalues. So that's really nice. The eigenspaces are mutually orthogonal. That is that the vectors from different eigenspaces are orthogonal. And A is orthogonally diagonalizable. So this is a different way of applying this this breakdown of the spectral decomposition. It comes out nice because a lot of the products, because it's orthonormal, a lot of the products end up being 0. And what we end up doing is we can take the eigenvalues, we can rewrite the matrix A not just as a product here, but as a sum of matrices. And the sum involves eigenvalues times the product of the eigenvectors. This kind of product, though, is a little bit different. This, it looks like we've seen like U1 transpose U1, like U1 transpose U1. That looks something like this. 1 0 0 0 0 1 or something like that. And if you do the dot product, it's a lot like the dot product. It's a different way of writing the dot product, and we just get out a number. But this is different. This is let me do 1 2 3 1 2 3, and what we get out here, we have a row of one number, we multiply it by a row of one number, so we get a crammed matrix. So we get 1 times 1, then we get 1 times 2, which is 2, then we get 1 times 3, which is 3. Then we have 2 times 1, which is 2, 2 times 2, which is 4, 2 times 3 is 6, 3 times 1 is 3, 3 times 2 is 6, 3 times 3 is 9. So the way this is set up, the U times U transpose, you get an n by n matrix if you have n entries in your vector. And at first, it's not a very interesting matrix. It's rank 1. All of the vectors, as long as U isn't the 0 vector, then you end up with a rank 1 matrix. All of the rows are linear, are scalar multiples of the first row, and all the columns are scalar multiple of the first column. So not very interesting. Pretty kind of simple in some ways. And what this says is that we can rewrite A as a sum of eigenvalues times a bunch of these rank 1 matrices. And the rank 1 matrices are these special products. This is sometimes called an outer product of these vectors, where the dot product is sometimes called an inner product. But these are the outer products. So this is just applying the theorem to the first example that we did when we broke it down, where we had eigenvalues of a -3, a -3, and 1, and a -3 corresponded to this eigenvector. It also corresponded to this eigenvector, normalized, and 1 corresponded, an eigenvalue of 1 corresponded to this eigenvector, and so they just wrote it out. And if you multiply those, if you take those products of the vectors of this outer product thing, then you get these matrices here, and A will equal those matrices. And this decomposition can help a lot to help make sense of what's going on with A. So sometimes this is quite powerful in doing this, and breaking it down to the sums of the sum or differences of these scaled matrices. Okay. This is just another example, so you don't have to spend time on this. You can go ahead and pause the video or take time looking through this. It is an example we already did the math for to figure out what the vectors were, and it just goes through and walks through it. So, okay, thank you very much.